Imagine being able to build an app with your name on it, just by thinking about it. Meet Base 44.
In this video, we're going to talk about Prometheus. So first, I'm going to explain to you what Prometheus is and what are different use cases where Prometheus is used and why is it such an important tool in modern infrastructure. We're going to go through Prometheus architecture, so different components that it contains. We're going to see an example configuration and also some of these key characteristics, why it became so widely accepted and popular, especially in containerized environments. Prometheus was created to monitor highly dynamic container environments like Kubernetes, Docker Swarm, etc. However, it can also be used in a traditional non-container infrastructure where you have just bare servers with applications deployed directly on it. So over the past years, Prometheus has become the mainstream monitoring tool of choice in container and microservice world. So let's see why Prometheus is so important in such infrastructure and what are some of its use cases. Modern DevOps is becoming more and more complex to handle manually and therefore needs more automation. So typically you have multiple servers that run containerized applications and there are hundreds of different processes running on that infrastructure and things are interconnected. So maintaining such setup to run smoothly and without application downtimes is very challenging. Imagine having such a complex infrastructure with loads of servers distributed over many locations and you have no insight of what is happening on hardware level or on application level, like errors, response latency, hardware down or overloaded, maybe running out of resources, etc. In such complex infrastructure, there are more things that can go wrong. When you have tons of services and applications deployed, any one of them can crash and cause failure of other services. And when you have so many moving pieces and suddenly application becomes unavailable to users, you must quickly identify what exactly out of these 100 different things went wrong. And that could be difficult and time consuming when debugging the system manually. So let's take a specific example. Say one specific server ran out of memory and kicked off a running container that was responsible for providing database sync between two database pods in a Kubernetes cluster. That in turn caused those two database pods to fail. That database was used by an authentication service that also stopped working because the database became unavailable. And then application that depended on that authentication service couldn't authenticate users in the UI anymore. But from a user perspective, all you see is error in the UI. Can't log in. So how do you know what actually went wrong? When you don't have any insight of what's going on inside the cluster, you don't see that red line of the chain of events as displayed here. You just see the error. So now you start working backwards from there to find the cause and fix it. So you check, is the application back and running? Does it show an exception? Is the authentication service running? Did it crash? Why did it crash? And all the way to the initial container failure. But what will make this searching the problem process more efficient would be to have a tool that constantly monitors whether services are running and alerts the maintainers as soon as one service crashes. So you know exactly what happened. Or even better, it identifies problems before they even occur and alerts the system administrators responsible for that infrastructure to prevent that issue. So for example, in this case, it would check regularly the status of memory usage on each server. And when on one of the servers it spikes over, for example, 70% for over an hour or keeps increasing, notify about the risk that the memory on that server might soon run out. Or let's consider another scenario where suddenly you stop seeing logs for your application because Elasticsearch doesn't accept any new logs because the server ran out of disk space or Elasticsearch reached the storage limit that was allocated for it. Again, the monitoring tool would check continuously the storage space and compare with the Elasticsearch consumption of space of storage.
I can't stop looking at you.
and it will see the risk and notify maintainers of the possible storage issue. And you can tell the monitoring tool what that critical point is when the alert should be triggered. For example, if you have a very important application that absolutely can have any log data loss, you may be very strict and want to take measures as soon as 50 or 60% capacity is reached. Or maybe you know adding more storage space will take long because it's a bureaucratic process in your organization where you need approval of some IT department and several other people. Then maybe you also want to be notified earlier about the possible storage issue so that you have more time to fix it. Or a third scenario where application suddenly becomes too slow because one service breaks down and starts sending hundreds of error messages in a loop across the network that creates high network traffic and slows down other services too. Having a tool that detects such spikes in network load plus tells you which service is responsible for causing it can give you timely alert to fix the issue. And such automated monitoring and alerting is exactly what Prometheus offers as a part of a modern DevOps workflow. So how does Prometheus actually work? Or how does it architecture actually looks like? At its core, Prometheus has the main component called Prometheus Server that does the actual monitoring work and is made up of 3 parts. It has a time series database that stores all the metrics data like current CPU usage or number of exceptions in an application. Second, it has a data retrieval worker that is responsible for getting or pulling those metrics from applications, services, servers, and other target resources and storing them or pushing them into that database. And third, it has a web server or server API that accepts queries for that stored data. And that web server component or the server API is used to display the data in a dashboard or UI, either through Prometheus dashboard or some other data visualization tool like Grafana. So the Prometheus server monitors a particular thing. And that thing could be anything. It could be an entire Linux server or Windows server. It could be a standalone Apache server, a single application or service like a database. And those things that Prometheus monitors are called targets. And each target has units of monitoring. For a Linux server target, it could be a current CPU status, its memory usage, disk space usage, etc. For an application, for example, it could be number of exceptions, number of requests, or request duration. And that unit that you would like to monitor for a specific target is called a metric. And metrics are what gets saved into Prometheus database component. Prometheus defines human-readable text-based format for these metrics. Metrics entries or data has type and help attributes to increase its readability. So help is basically a description that just describes what the metrics is about, and type is one of 3 metrics types. For metrics about how many times something happened, like number of exceptions that application had or number of requests it has received, there is a counter type. Metric that can go both up and down is represented by a gauge. Example, what is the current value of CPU usage now? Or what is the current capacity of disk space now? Or what is the number of concurrent requests at that given moment? And for tracking how long something took or how big, for example, the size of a request was, there is a histogram type. So now the interesting question is, how does Prometheus actually collect those metrics from the targets? Prometheus pulls metrics data from the targets from an HTTP endpoint, which by default is host address/metrics. And for that to work, 1, targets must expose that /metrics endpoint, and 2, data available at /metrics endpoint must be in the format that Prometheus understands. And we saw that example metrics before. Some servers are already exposing Prometheus endpoints, so you don't need extra work to gather metrics from them. But many services don't have native Prometheus endpoints, so extra component is required to do that. And this component is exporter. So exporter is basically a script or a service that fetches metrics from your target and converts them in format Prometheus understands and exposes this converted data at its own /metrics endpoint, where Prometheus can scrape them. And Prometheus has a list of exporters for different services like MySQL, Elasticsearch, Linux server, build tools, cloud platforms, and so on. I will put the link to Prometheus official documentation and exporter list as well as its repository in the description. So for example, if you want to monitor a Linux server, you can download a node exporter tar file from Prometheus repository. You can untar and execute it, and it will start converting the metrics of the server and making them scrapable at its own /metrics endpoint. And then you can go and configure Prometheus to scrape that endpoint. And these exporters are also available as Docker images. So for example, if you want to monitor your MySQL container in Kubernetes cluster, you can deploy a sidecar container of MySQL exporter that will run inside the pod with MySQL container, connect to it and start translating MySQL metrics for Prometheus and making them available at its own /metrics endpoint. And again, once you add MySQL exporter endpoint to Prometheus configuration, Prometheus will start collecting those metrics and saving them in its database. What about monitoring your own applications? Let's say you want to see how many requests your application is getting at different times, or how many exceptions are occurring, how many server resources your application is using, etc. For this use case, there are Prometheus client libraries for different languages like Node.js, Java, etc. Using these libraries, you can expose the /metrics scraping endpoint in your application and provide different metrics that are relevant for you on that endpoint. And this is a pretty convenient way for the infrastructure team to tell developers, emit metrics that are relevant to you, and we'll collect and monitor them in our infrastructure. And I will also link the list of client libraries Prometheus supports, where you can see the documentation of how to use them.
Hello， 大家好，我叫俊。近期很多朋友问我私讯我有关于交易的问题啊，因为我最近有个账号一个月做了100%，他就问我说，一年正
use them. So I mentioned that Prometheus pulls this data from endpoints, and that's actually an important characteristic of Prometheus. And let's see why. Most monitoring systems like Amazon CloudWatch or New Relic, etc., use a push system, meaning applications and servers are responsible for pushing their metric data to a centralized collection platform of that monitoring tool. So when you're working with many microservices and you have each service pushing their metrics to the monitoring system, it creates a high load of traffic within your infrastructure, and your monitoring can actually become your bottleneck. So you have monitoring, which is great, but you pay the price of overloading your infrastructure with constant push requests from all the services, and thus flooding the network. Plus, you also have to install daemons on each of these targets to push the metrics to monitoring server, while Prometheus requires just a scraping endpoint. And this way, metrics can also be pulled by multiple Prometheus instances. And another advantage of that is using pull, Prometheus can easily detect whether service is up and running, for example, when it doesn't respond on the pull or when the endpoint isn't available. While with push, if the service doesn't push any data or send its health status, it might have many reasons other than the service isn't running. It could be that network isn't working, the package got lost on the way, or some other problem. So you don't really have an insight of what happened. But there are a limited number of cases where a target that needs to be monitored runs only for a short time, so they aren't around long enough to be scraped. Example could be a batch job or scheduled job that, say, cleans up some old data or does backups, etc. For such jobs, Prometheus offers push gateway component so that these services can push their metrics directly to Prometheus database. But obviously using push gateway to gather metrics in Prometheus should be an exception, because of the reasons I mentioned earlier. So how does Prometheus know what to scrape and when? All that is configured in Prometheus.yaml configuration file. So you define which targets Prometheus should scrape and at what interval. Prometheus then uses a service discovery mechanism to find those target endpoints. When you first download and install Prometheus, you will see the sample config file with some default values in it. Here's an example where you have global config that defines scrape interval or how often Prometheus will scrape its targets. And you can override this for individual targets. The rule files block specifies the location of any rules we want Prometheus server to load, and the rules are basically either for aggregating metrics values or creating alerts when some condition is met, like CPU usage reached 80%, for example. So Prometheus uses rules to create new time series entries and to generate alerts. And the evaluation interval option in global config defines how often Prometheus will evaluate these rules. And the last block, scrape configs, controls what resources Prometheus monitors. This is where you define the targets. Since Prometheus has its own metrics endpoint to expose its own data, it can monitor its own health. So in this default configuration, there is a single job called Prometheus, which scrapes the metrics exposed by the Prometheus server. So it has a single target at localhost 1990, and Prometheus expects metrics to be available on that target on a path of /metrics, which is a default path that is configured for that endpoint. And here you can also define other endpoints to scrape through jobs. So you can create another job and, for example, override the scrape interval from the global configuration and define the target host address. So a couple of important points here. So the first one is, how does Prometheus actually trigger the alerts that are defined by rules and who receives them? Prometheus has a component called Alert Manager that is responsible for firing alerts via different channels. It could be email, it could be a Slack channel, or some other notification client. So Prometheus server will read the alert rules, and if the condition in the rules is met, an alert gets fired through that configured channel. And the second one is Prometheus data storage. Where does Prometheus store all this data that it collects and then aggregates? And how can other systems access this data? Prometheus stores the metrics data on disk, so it includes a local on-disk time series database, but also optionally integrates with remote storage system. And the data is stored in a custom time series format. And because of that, you can't write Prometheus data directly into a relational database, for example. So once you've collected the metrics, Prometheus also lets you query the metrics data on targets through its server API using PromQL query language.
If you want to learn how to edit really well from professional Hollywood editors, we're going to show you the stuff that nobody else is teaching.
You can use Prometheus dashboard UI to ask the Prometheus server via PromQL to, for example, show the status of a particular target right now, or you can use more powerful data visualization tools like Grafana to display the data, which under the hood also uses PromQL to get the data out of Prometheus. And this is an example of a PromQL query, which this one here basically queries all HTTP status codes except the ones in 400 range. And this one basically does some subquery on that for a period of 30 minutes. And this is just to give you an example of how this query language look like. But with Grafana, instead of writing PromQL queries directly into the Prometheus server, you basically have Grafana UI where you can create dashboards that can then, in the background, use PromQL to query the data that you want to display. Now, concerning PromQL, the Prometheus configuration and Grafana UI, I have to say from my personal experience that configuring Prometheus YAML file to scrape different targets and then creating all those dashboards to display meaningful data out of the scraped metrics can actually be pretty complex, and it's also not very well documented. So there is some steep learning curve to learning how to correctly configure Prometheus and how to then query the collected metrics data to create dashboards. So I will make a separate video where I configure Prometheus to monitor Kubernetes services to show some of the practical examples. And the final point is an important characteristic of Prometheus, that it is designed to be reliable even when other systems have an outage, so that you can diagnose the problems and fix them. So each Prometheus server is standalone and self-containing, meaning it doesn't depend on network storage or other remote services. It's meant to work when other parts of the infrastructure are broken, and you don't need to set up extensive infrastructure to use it, which of course is a great thing. However, it also has disadvantage that Prometheus can be difficult to scale. So when you have hundreds of servers, you might want to have multiple Prometheus servers that somewhere aggregate all this metrics data, and configuring that and scaling Prometheus in that way can actually be very difficult because of this characteristic. So while using a single node is less complex and you can get started very easily, it puts a limit on the number of metrics that can be monitored by Prometheus. So to work around that, you either increase the capacity of the Prometheus server so it can store more metrics data, or you limit the number of metrics that Prometheus collects from the applications to keep it down to only the relevant ones. And finally, in terms of Prometheus with Docker and Kubernetes, as I mentioned throughout the video with different examples, Prometheus is fully compatible with both, and Prometheus components are available as Docker images and therefore can easily be deployed in Kubernetes or other container environments. And it integrates great with Kubernetes infrastructure, providing cluster node resource monitoring out of the box, which means once it's deployed on Kubernetes, it starts gathering metrics data on each Kubernetes node server without any extra configuration. And I will make a separate video on how to deploy and configure Prometheus to monitor your Kubernetes. By the end of this video, you will know not only what Nginx is, but also why it was created and what it's used for with real-life examples. Back in the day, when the web was still simple with less users, the basic use case was a browser requested a web page from one web server. The web server was a server machine that had a software installed on it that assembled the page and sent it back to the browser, which then displayed it to the user. A piece of software that runs on a server machine and can respond to requests from a browser. And that web server software, that was Nginx, a piece of software that runs on a server machine and can respond to requests from a browser. Then web became popular, so you had thousands or millions of requests per website. Imagine one single server handling millions of requests. That's way over the technical limit of a server software. Well, we need a few more servers to handle that load. So we added 10 Nginx web servers. But now we need something that determines where requests from the browser end, which one of those 10 servers will handle them. And that's where load balancing comes in. So the same Nginx web server becomes a load balancer that proxies the requests to those 10 web servers. And by the way, the word proxy means to do something on someone else's behalf. So it accepts the browser requests on behalf of the web servers. So it sits at the entry like a concierge and then distributes the load among the web servers. Now, how does it distribute the load? That depends on whichever algorithm was configured on it. It could be a simple logic, such as just whichever server is least busy gets the request, or it could be a round robin, which is a popular algorithm that basically distributes the requests equally in a cyclical manner. So very simple load balancing logic. So now we have Nginx as web server software and the proxy as well. And that load balancing is just one of the functionalities of Nginx proxy. So it's the same server and technology, but with a different task now. So what are those other features or functionalities of a proxy? Imagine New York Times article comes out and millions of people open it on their laptops in the browser. Now imagine every time the request landed with one of the web servers that assembled the response, like put the images together, get them from a database, put text and paragraphs and everything together, edit all the links, sent it back as a response. And this happened a million times. Pretty inefficient, right? Instead, it makes sense to assemble this article, get all the data from a database, put the text and links and everything together once and store it. It's a static article. It's not going to change, right? So just keep one final copy and send it to everyone who requests it. That's caching functionality. And it is another main feature of Nginx proxy server. So you can configure caching on Nginx proxy so you don't have to hit the database or the web servers every time a request comes in. It will just return that cached file. Now imagine we have comes in, so you don't have to hit the database or the web servers every time a request comes in. It will just return that cached file. Now imagine we have 100 servers of an online banking application or a social network like Facebook. That makes those servers a pretty juicy target for hackers. They all want to hack into your servers and get the treasure, which is payment data, personal data, passwords, and so on. Now imagine you exposed all 100 servers to public access. So basically all those requests can directly hit each of the web servers. If you do that, you actually make work for hackers so much easier. They would need to find just one issue in one of those 100 servers, and they could potentially break into your entire system. Because all your servers are publicly accessible directly, they can just ping the hell out of them and probe them until they find an issue or an entry because you forgot to update a library or a software package, and they can hack your web server application. So you have to worry about absolutely perfectly securing 100 servers. Now instead, we just give them one server that is the only one that's publicly accessible. You can put all your tightest security efforts on one server instead of 100 servers. And this way, having one entry point, which is the proxy, as publicly accessible entry point reduces the security attack surface tremendously and basically acts like a shield or security layer before all those web servers. So in addition to load balancing and caching, a very, very important functionality of a proxy is an added security for your web servers. Now, talking about security, I mentioned that since we have one entry point, we can focus all our efforts to securing that one proxy server in all aspects. And one important security measure is encrypted communication. So frontend will send encrypted message to the proxy, which means even if an attacker sees that traffic on user's browser or during the transmission, they can't read it. Only the proxy server can decrypt it. But again, for added security, in many systems, proxy that acts as a shield, a security shield, will simply pass on that encrypted message to the web servers, and the web server will decrypt it itself, which is actually a better security practice. So here, the functionality of a proxy is to be able to accept encrypted traffic with SSL encryption. So you can configure your proxy to deny any request that is not encrypted and only accept encrypted requests. Now imagine Netflix, which, by the way, uses Nginx in its backend. And as we know, Netflix has millions of users, so it's getting millions of requests for videos on its web servers. And let's say it's an evening in New York, millions of people come home after work, all at the same time. They switch on Netflix and start watching the most popular series at that time. That means suddenly at the very same time, millions of requests for a high quality video is sent to Netflix. So in this case, imagine that Nginx proxy server would have to send back the entire high quality video to millions of users at once. That's a lot of bandwidth. Imagine how long it would take to send it over the internet cables. all the way to the TVs of millions of viewers. That's where compression helps. Nginx proxy can also be configured to compress large images or video files to save bandwidth both on the side of the clients, so people who are receiving those large files, but also on the server side, who is sending all that content. So it arrives faster and it uses up less of your internet bandwidth. And as part of it, it also supports sending responses in chunks instead of the entire file at once. So basically, it sends you part of the video, and then by the time you have watched the first half, the second half of the video has been sent over to you as well. So these are all the functionalities that you can configure for Nginx as a proxy server. Now, you may be thinking, how do you make Nginx do all these things? How do you configure them? How do you tell Nginx whether it should act as a web server or a proxy server? And how do you configure all this caching and SSL traffic and all this stuff? Well, that's where Nginx configuration file comes in, which lets you define all this configuration with so-called directives. This is where you can define whether you want your Nginx to be a web server or a proxy server, simply by configuring whether it should forward the traffic to other web servers or whether it should handle it itself. You can configure which port you want Nginx server to listen on. This is an example of a simple web server configuration that listens on port 80, and with location basically defines from where in the file system it should serve those static files back to the browser. But as we learned, communicating on port 80 or HTTP port is insecure. Instead, we want to encrypt all the communication. And you can configure that easily in Nginx to route any traffic coming on port 80 to HTTPS by sending those requests to HTTPS endpoint. And here we have an HTTPS server configured that serves the files as well as specifies the SSL certificate location, the public key and the private key for the SSL communication. And it listens on the HTTPS port 443. So that's a simple configuration that allows you to tweak Nginx to handle requests like that. You also have its own configuration to configure load balancing to multiple backend servers. And within that configuration, you can also define which load balancing algorithm to use, like select the least busy server or use the default one, which is round robin, which, as I said, just equally distributes the load in a cyclical order between those servers. You also have the caching configuration with multiple different elements, like how long the cache should be stored before it's refreshed, and so on. And as you see, the configuration of all these functionalities is pretty straightforward, and it's also pretty granular. Like, you can do tons of different configuration with Nginx, and you actually have a full list of all those configuration blocks and directives in this list here, which is a pretty huge list. And as you see, the configurations for proxy functionalities have proxy prefix, so you can differentiate them as well. Now, Nginx is very flexible, as you see, and super fast as well. So it became very popular in containers as well, and made its way as one of the most popular solutions for Kubernetes ingress controller functionality. Ingress controller is essentially a proxy with advanced load balancing functionality, but for Kubernetes. So what Nginx was doing for simple web servers, it's now doing for Kubernetes cluster in the form of ingress controller, acting as a proxy and load balancer that receives the incoming traffic first, and then based on the configuration that we define, forwards it to the right service inside the cluster. Now, this load balancing configuration, as well as the logic, is more advanced and more Kubernetes specific, but the idea is pretty much the same. And I actually have full videos on ingress and ingress controller and how to configure it you can watch on my channel. In fact, I create these tutorials regularly on a lot of interesting technologies. So if you want to educate yourself in tech, make sure to subscribe and activate notification to get those new tutorial videos. Now, there are actually many ingress controller implementations out there for Kubernetes, but Nginx is one of the most popular ones. And I have actually used Nginx ingress controller in most of my projects as well. Now, some of you may be thinking, doesn't each cloud platform have its own load balancer? Why do I need Nginx as a load balancer? Well, you actually need both. Nginx Ingress Controller, which acts as a load balancer, is used inside the cluster. So unlike the proxy for web servers, it's not publicly accessible, so you can't access the Nginx Ingress Controller directly from the browser. It actually lives inside the cluster network and forwards the requests internally. So who is getting the requests from public? What is the public entry point for the browser requests? That's the cloud load balancer, like AWS ELB, for example, which then forwards that request to the Ingress controller inside the cluster. And this is important because it adds a very important security layer to those requests, so the cluster component is never directly exposed to public access. Instead, every request comes from the cloud load balancer, which then forwards it to the Ingress controller within the cluster, which then routes the traffic based on intelligent logic to different applications within the cluster. And with intelligent routing, what I mean is if you have one large application with lots of sub-segments or microservices, for example, you can configure your Ingress controller so if the request URL includes online cart, it routes the traffic to online cart microservice. If it includes payment, it routes the traffic to payment service, and so on. Now, some of you who've been in IT for a little longer may have worked with Apache Web Server. So what's the difference between Apache Web Server and Nginx Web Server? Well, not much actually. Nginx and Apache Web Servers do pretty much the same thing. Just like Nginx, Apache also used to be a basic web server, and then they extended its functionality as a proxy. And it has all these benefits and functionalities of a proxy that we discussed. Apache was actually already widely used when Nginx was created. And the major benefit of Nginx was that it was faster, more lightweight, and definitely had an advantage when it came to serving huge amounts of static files. Plus, as you saw, it has a pretty easy configuration as well. And Nginx also became more popular in the container world. Now, I hope you got a clear overview of what Nginx is, and hope I've answered all the questions you may have had while learning about Nginx. And with that, thank you for watching and see you in the next video. In this lecture, we're going to learn about a very important concept in the IT world, which is virtualization and virtual machines. We're going to see what virtual machines are and why are they so useful, and learn all the main concepts of virtualization. Once we learn the concept of how virtual machines work, we're going to see it in action in the demo part by creating a Linux virtual machine on our computer using a popular open source software called VirtualBox. I'm Nana, and I have taught hundreds of thousands of people around the world how to advance their DevOps skills through my YouTube videos, online courses, and the 6-month DevOps Bootcamp. If you're new here, be sure to subscribe as I upload new videos all the time. Now let's see what a virtual machine is. Imagine you have a Windows computer, and as we learned, a computer has hardware like CPU, RAM, and storage. So we would have a Windows operating system on top of that controls how applications use these hardware resources. And on top of the Windows operating system, you would have applications that talk to Windows. So everything's cool here. Now, what if you wanted to use Linux instead? Maybe for your work, or maybe you just want to learn a new operating system. For that, you would need a machine with hardware resources and Linux operating system on top of that. And then you could run applications on that Linux operating system. So basically you would need another computer, another laptop where you would install that Linux operating system. Now, what virtualization is that you don't need a separate physical hardware or physical computer to install an operating system. You can install Linux operating system on top of the Windows OS or vice versa. You can install Windows on Linux or Windows and Linux on Mac OS. You can do any combination basically. You can even do Windows on Windows or Linux on Linux. And you can achieve that using something called a hypervisor. Hypervisor is a technology that allows hosting multiple virtual computers on a physical computer on top of the operating system that you already have installed. And one of the most popular hypervisors out there is VirtualBox from Oracle. And one of the main reasons for its popularity is because it's open source, and VirtualBox actually works on all operating systems. And it's pretty easy to use. So VirtualBox will let you create a virtual computer on your Windows computer by telling the Windows operating system, hey, can I have some of your hardware resources that you manage to create a virtual CPU, virtual RAM, virtual storage for my virtual computer? And as I said, you can have multiple virtual machines that are running on your computer through a hypervisor. Now, note here that you can only give the virtual computer the hardware resources you actually have available on that computer. If you have 8 gigabytes of RAM and your Windows is using 4 gigabytes and you give your virtual machine another 4 gigabytes, then you have no RAM left to be used for another virtual machine, so you can't create another one. So basically now you are sharing the hardware resources of one machine to run multiple virtual machines. So this means that as long as you have one computer with one operating system, using the hypervisor like VirtualBox, you can install other operating systems on top of it. But these virtual machines actually don't see each other and they're completely isolated. So the virtual machine itself thinks that it is an independent computer. It's the only one running on that computer. It doesn't even know that it's a virtual machine. And it doesn't know that it's hosted on top of another operating system. And that separation is actually great because if something happens to that virtual machine, something breaks inside or someone hacks inside that virtual machine, it won't affect the main operating system. The main OS probably won't even know that the VM has some issues, and it doesn't care. So when this happens, you can just delete that VM and create a fresh new one super easily. Now, you're probably asking, what is it actually good for? What is the usage or benefits of having a hypervisor and having virtual machines on your computer? First of all, it's really great for learning new operating systems. So now you don't have to go and buy a new computer and install Linux on it. You can basically just host it on your Windows machine if you want to. Maybe you want to just experiment and play around with an operating system, but you don't want to actually destroy or endanger your main operating system. So you can quickly spin up a virtual machine, you can play around with it and do all the stuff that you want. And then once you're done with it, you can just basically remove it. Another great use case for virtual machines is if you want to test an application, like a web application that you're developing. Maybe you want to see how that works and how it looks like in different operating systems, in different browsers. So you may be developing on a Mac OS laptop and you want to see how your application performs on Linux machine in a Firefox browser. And you may also want to see how your application runs on Windows in an Internet Explorer browser. So you can create virtual machines for both of these combinations and test your application there. And when you're done, you can just delete them. Before moving on, I want to give a shout out to Kasten, who made this video possible. Kasten's K10 is the data management platform for Kubernetes. K10 basically takes off most of the load of doing backup and restore in Kubernetes from the cluster administrators. It has a very simple UI, so it's super easy to work with, and has an intelligent logic which does all the heavy lifting for you. For my viewers, Kasten provided an ebook, Kubernetes Backup and Recovery for Dummies, which you can download for free. So be sure to check out the link in the video description. And now let's see what's the difference between type 1 and type 2 hypervisors. And this type of hypervisor that I just described, which is basically creating virtual machines on top of an existing operating system, is called a type 2 hypervisor. So you have the host operating system, or the main operating system, which is already installed on the hardware on your machine. On that operating system, you install a hypervisor like VirtualBox, right? So on Windows, you install your VirtualBox, and then using the VirtualBox, you can now install guest operating systems. And the guest operating systems, as I said, will borrow the hardware resources from the host operating system. And the Type 2 hypervisors are typically used for personal computers for the use cases that I just described. However, for big servers that companies are using, you have the second type of hypervisor, which is Type 1 hypervisor, which actually works in exactly the same way. However, the main difference here is that instead of installing a hypervisor on a host operating system, you basically install it directly on the hardware. And that's why the Type 1 hypervisors are also called bare metal hypervisors. So the hypervisor actually controls the hardware resources instead of talking to the host operating system whether it can borrow the resources for its virtual machines. So it sits directly on top of that hardware and controls everything. And some of the popular examples of Type 1 hypervisors are VMware ESXi or Microsoft's Hyper-V. And once installed, basically the concept is the same as with Type 2 hypervisors. You basically just install any operating system on top of it. So for big servers, you'll have one physical server with a bare metal hypervisor installed on it, and then you would have multiple virtual machines that are running on that hypervisor, all sharing the same hardware resources. And Type 1 hypervisor is mostly what those big companies and big cloud platforms actually use to create and run their whole infrastructure. So when you create a server instance on a cloud platform like AWS or DigitalOcean or Google Cloud or whatever platform, you're creating these virtual machines on a physical server. And other users who create an instance may get a virtual machine on the same exact physical server as your virtual machine. But as I said, these VMs are completely isolated. They don't know anything about each other. So if something happens in one virtual machine, if someone gets hacked whose VM is on the same physical server, you won't even know it because each VM is running in its own isolated environment, right? They don't share a network, they don't share any resources, they don't share anything. They're completely independent from each other. Now, I give you some examples of why Type 2, or also called hosted hypervisors, are useful, right? For using them on personal computer. But what are the use cases of the Type 1 hypervisors? So what is basically the big advantage of companies going out there and using this virtualization on their server infrastructure? One big advantage of using virtualization and hosting multiple virtual machines on one physical machine is efficient usage of hardware resources. Because now you may have these performant big servers on a cloud, but you can actually, or a cloud provider can actually let the users put together any combination of resources they want in their instance by picking and choosing how much CPU, how much RAM, how much storage they want. So they have this flexibility of choosing the size of their instances because everything is virtualized, right? The RAM and CPU and storage, so all of these resources are virtualized. So that's one big flexibility. So now the cloud providers, they can actually use up all their physical server resources by actually dividing them into small pieces that are then used by virtual machines. Now there is one more very important benefit and basically transformation that happened in IT industry because of virtualization. And that is basically abstracting away the operating system that is running on the hardware from the hardware itself. And that abstraction actually is a really big deal. And let's see why. So before virtualization, when a company had a server, like their own database server or a server where Jenkins was running, they would manage it themselves, like install an operating system directly on it and then start installing applications on that operating system, like installing and configuring Jenkins or installing database application, etc. And when the operating system is installed directly on a hardware without that hypervisor layer in between, that operating system is then tightly coupled to the hardware. That means if the hardware component of the computer failed, like the hard disk exploded or the motherboard failed, whatever, and you couldn't replace that component because maybe it was an old server and you couldn't find that component anymore, or maybe it was just not repairable anymore for whatever reasons, it meant your whole computer would be useless and the operating system and the applications you installed and configured on it and all the data would be gone. So relying on that one physical box meant one point of failure and therefore high risk of losing all the services running on that machine. With virtualization, however, you have your operating system as a portable file that you can move around. And these files are virtual machine images. So that portable file, that image, will have the operating system, all the applications, the browser applications, the editors, Jenkins, whatever applications you would usually install on an operating system, all the configuration, files, pictures, documents, basically everything would be inside that portable file. And since it's a file, just like a picture or a text document, you can make copies of it and you can have backups of it, which is amazing and really useful, especially for companies. That means you could take your whole Jenkins server operating system and pack it into this portable image where all your Jenkins configuration, all your plugins, all your data basically would be inside, exactly as you configured it, and you can make backups of that image, which are called snapshots, right? So you'd have operating system image snapshots. So now if something happens to that virtual image where Jenkins is running, like you mess up Jenkins configuration or someone hacked into it or the hardware breaks, you can simply take that snapshot, that operating system image, and simply run it on a different computer with hypervisor on it. So by containing the operating system and the application layer of it in a portable file, you can secure your application and your work very easily. And you can move it around machines without being dependent on any physical server. So the virtual machines and the virtualization concept generally is very powerful, and that's why you see it everywhere in IT. It has completely changed the way we work, so whether you want to become a cloud engineer, a system administrator, software developer, or DevOps engineer, you need to understand the virtualization because you will be working with virtual machines. This video is actually a small part of a Linux module in the complete DevOps educational program. Linux is an important prerequisite for DevOps engineers. So in the Linux module, you learn everything you need to know about operating systems and Linux as a DevOps engineer. So if you want to become a DevOps engineer or build up your DevOps skills from zero to knowing all the required DevOps concepts and tools, be sure to check out our bootcamp and learn from a Docker Captain, AWS Container Hero, and CNCF Ambassador. With that, thank you for watching. I hope you learned a lot. In this video, we're going to talk about Terraform. First, I'm going to explain to you what Terraform is and what it's used for. Then we will see what is the difference between Terraform and Ansible and when to use each. We will also look at the Terraform architecture and command as well as an example Terraform configuration file. After which you will have a good overview and understanding of how Terraform actually works and how it does its job. So first of all, what is Terraform? Terraform allows you to automate and manage your infrastructure and your platform and services that run on that infrastructure. It's open source and it uses declarative language, meaning you don't have to define every step of how this automation and management is done. You just declare what you want, the final result or end result, and Terraform will figure out how to execute it, versus imperative style where you specify how to execute each step. So as I said, Terraform is a tool for infrastructure provisioning. So what does it mean exactly? Let's say you just started a project where you create some application and you want to set up an infrastructure from scratch where this application will run. How does your infrastructure look like? Let's say you want to spin up several servers where you will deploy your 5 microservice applications that make up your application as Docker containers, and also you're going to deploy a database container. You decide to use AWS platform to build your whole infrastructure on. So first step will be to go to AWS and prepare this setup so the applications can be deployed there. This means you create your private network space, you create and deploy server EC2 server instances, you install Docker on each one of those, plus any other tools that you might need for your application. You set up security on your servers, like firewalls, you set up network, etc. Once the infrastructure is prepared, you can now deploy your Docker applications or Docker containers on that prepared infrastructure. So as you see, these are 2 different tasks or 2 separate steps of creating the whole setup. One is provisioning the infrastructure, preparing everything so the application can be deployed. The second one is actually deploying the applications on it. So you might even have 2 separate teams or 2 individuals who do these 2 separate tasks. So possible scenario, a DevOps team member configures the infrastructure and a developer then deploys the applications on the prepared infrastructure. So where does Terraform come into this whole thing? Terraform is used for the first part, where you provision the infrastructure to prepare it for the application deployment. Creating the VPC, spinning up the servers, creating the security, the AWS user with its permissions, maybe installing Docker, specific version on the servers, etc. And obviously all of this needs to be done in the correct order because one task maybe depends on the other. Now here I must mention something that a lot of people ask when it comes to Terraform, and that is, what is the difference between Ansible and Terraform? Because they seem to be doing the same thing, especially if you read the official definitions or official documentation, they sound like the same tools. So the question is pretty logical. What is the difference between them and which one should I use for my project? So let's see the similarities and differences between these two, using our example setup. First of all, Terraform and Ansible are both infrastructure as a code, meaning they're both used to automate provisioning, configuring, and managing the infrastructure. However, Terraform is mainly infrastructure provisioning tool. That's where its main power lies. But it also has possibilities to deploy applications and other tools on that infrastructure. Ansible, on the other hand, is mainly a configuration tool. So once the infrastructure is provisioned and it's there, Ansible can now be used to configure it and deploy applications, install and update software on that infrastructure, etc. So as you see, there are overlaps of what each tool does, and this creates the confusion. Other differences to consider in terms of those overlaps are Ansible is more mature, and Terraform is relatively new, and because of that, it's also changing dynamically. And Terraform is much more advanced in orchestration. So to summarize the difference, Terraform is a better tool for provisioning infrastructure, and Ansible is a better tool for configuring that infrastructure, deploying, installing applications and services on them. So it's a common practice where DevOps engineers use the combination of these tools to cover the whole setup end-to-end, using both for their own strengths, instead of just using one tool. Now, if you want to learn more about Ansible as well, I have my own video that I made about it, where I explain exactly what Ansible is and how to use it, so you can check it out. And I will also create another video where I will compare the infrastructure as a code tools, like Ansible, Chef, Terraform, CloudFormation, etc., in more detail, and also explain why each is best in one area, even though they can do other tasks as well. So if you want to see those videos and if you want to learn more, then you can subscribe to my channel, you can click the notification bell, and stay tuned for the upcoming videos as well. So now let's go back to our use case where we created the infrastructure using Terraform and on AWS, provisioned successfully for a project, and you deployed the application on it. Now you decide that you want to add 5 more servers to the existing infrastructure to deploy more microservices because your team developed some more features and they need to be deployed. And you also want to add some security configuration, or maybe remove some stuff that you configured at the beginning. So now we are in the phase of managing the existing infrastructure, adding some stuff, reconfiguring, removing some stuff, etc. And using Terraform, you can make such adjustments to your infrastructure pretty easily. And this task of managing the infrastructure is just as important because once you've created the initial infrastructure for your project, you will be continually adjusting and changing it. And because of that, you also need some automation tool that will do most of the heavy lifting for you so that you don't have to manually configure and do some stuff. So once you are set up with Terraform to create and change and maintain your infrastructure, another useful thing or common use case could be replicating that infrastructure. Let's say after you have tested this setup and everything works fine, you decide now you want to release your application in production environment. So you want to create a production environment that replicates this exact setup and keep the first as a development environment where you can test new features, new microservices, and updates before you launch it into production. Again, you can use Terraform here to automate that process. So you can easily spin up an identical infrastructure and set up using the same Terraform code that you use for the first setup, the development environment setup. And you can do the same to spin up an identical staging server as well. So that makes these tasks also very easy. So how does Terraform do all this? How does Terraform actually connect to these infrastructure provider platforms and use all these technologies to provision stuff? So for example, how does Terraform connect to AWS to create virtual space, start EC2 instances, configure networking, etc.? In order to do the job, Terraform has 2 main components that make up its architecture. The first one is Terraform's core. And the core uses 2 input sources in order to do its job. So it takes Terraform configuration that you, as a user, write, and where you define what needs to be created or provisioned. And the second one is Terraform state, where Terraform keeps the up-to-date state of how the current setup of the infrastructure looks like. So what core then does is it takes this input and it figures out the plan of what needs to be done. So it compares the state, what is the current state, what is the configuration that you desire, the end result, as I mentioned at the beginning, and compares that, and when it sees there's a difference or you want something else than what the current state is, it figures out what needs to be done to get to that desired state in the configuration file. So what needs to be created, what needs to be updated, deleted, in which order on that infrastructure setup. And the second component, or the second part of the architecture, are providers for specific technologies. This could be cloud providers like AWS, Azure, or other infrastructure as a service platforms. So for the infrastructure level tasks. But Terraform, as I mentioned, has also providers for more high-level components like Kubernetes or other platform as a service tools, even some software as a service tool. So it gives you possibility to create stuff on different levels, like create an AWS infrastructure, then create Kubernetes on top of it, and then create services inside that or components inside that Kubernetes cluster. So it gives you all these possibilities. And it does that through those providers. Terraform has over 100 providers for these different technologies, and each provider then gives Terraform user access to its resources. So through AWS Provider, for example, you have access to hundreds of AWS resources like EC2 instances, the AWS users, etc. With Kubernetes Provider, you get access to Kubernetes resources like services and deployments and namespaces, etc. So this is how this works. And this way, Terraform tries to help you provision and cover the complete application setup, from infrastructure all the way to the application. And this is sure convenient, but as I mentioned in the comparison between Terraform and Ansible, Terraform's strength is actually in the infrastructure provisioning, and for the other stuff, you can use Ansible or similar tools. So once the core creates an execution plan based on the input from config file and state, it then uses providers for specific technologies to execute the plan, to connect to those platforms, and to actually carry out those execution steps. So now, to also have an idea of how Terraform configuration file looks like, this is an example where you see AWS provider is configured, and through the provider, you now have to AWS resource like VPC. You can create that with some attributes. The same way, you have the Kubernetes provider here configured, and through that now you can create a Kubernetes namespace resource where you pass some attributes. And the syntax is very intuitive, I would say. Basically, you define what you want. So you want a resource of a certain technology or a certain provider created, and then you would define its attributes, and that's what Terraform will create or do for you. Now, one thing I mentioned at the beginning, and I want to go into detail, is the declarative approach that Terraform's configuration files are written in. And this is important to understand. So what does declarative mean exactly? When you create a Terraform file, instead of defining what steps to be executed to create the VPC, or to spin up 5 EC2 instances, or create the network configuration, you define the end state you desire. So you say, I want 5 servers with network configuration like this, and I want one AWS user that has these permissions to access all the servers. Terraform, go do that for me. So instead of defining exactly what to do, which is an imperative approach, you define what the end result should be, a declarative approach. Now for the initial setup, this may not make much difference. So when you see the configuration of imperative and declarative approach, it might actually look pretty similar. But consider when you're updating your infrastructure, like removing a server or adding another server or making other adjustments. With imperative approach, you would say in the configuration file, remove 2 servers, add a firewall configuration, add some permissions to the AWS user, etc. So you give instructions of what to do. With declarative approach, like in Terraform example, you would say, my new desired state is now 7 servers, this firewall configuration, and user with this set of permissions. Do whatever needs to be done to get from the current state to the new desired state. So now you don't have to actually calculate and decide how many servers needs to be added. You just say, I want 7 servers at the end. That's what I want. Or you don't need to calculate and figure out how many permissions or which permissions you should add. You just say, I want this set of permissions to come out at the end. So with the declarative approach, you just adjust the old configuration file and re-execute it instead of adding the new set of instructions. This is obviously very comfortable because your configuration file stays clean and small, but also you always know what the current setup is just by looking at the configuration file, because that's always the end result. Whereas in the first approach, an imperative, you have to somehow add this up and figure out the delta between all the changes applied by multiple instructions. So, you've created a Terraform file, configuration file, that defines your desired infrastructure setup on AWS. Now, how do you make Terraform take action? Terraform has commands you can execute to go through different stages, which is pretty clear and straightforward. The first command is refresh. With this command, Terraform will query the infrastructure provider, in our case, AWS, to get the up-to-date state. So Terraform will now know what is the current state of the infrastructure. The next command is plan. Remember, I said the core is responsible for taking current state in your configuration file as input and decide based on the difference what needs to be done. That's the plan. So what Terraform needs to do in order to achieve the desired state that you define in the Terraform configuration file. If it's an initial setup, it figures out all the steps to create the desired setup. If it's an update, it compares the existing setup with the new desired state and figures out what changes and adjustments need to be made in which order to create the new desired state. For example, add a new server, add a new permission, etc. Now this is just a plan. This is where the core kind of constructs the plan logically, or what needs to be done. The next command is the command where the actual execution happens. And that's the apply command. So with apply, you can execute the plan. So plan command is like a preview of what's going to happen. If you execute apply, obviously Terraform in the background will do the refresh, get the up-to-date state, then create the plan, and then apply it. Which means if you want to execute a configuration file, you can just execute the apply command, and it will do all this. And another command is destroy, which obviously destroys the whole setup, removing elements one by one in the right order and cleaning up all the resources that were created. Basically reverting everything that has been created. And this could be used if, let's say, you created an environment for an important demo day, and you didn't want to interfere with the existing environments. Once the demo is over, you can destroy the whole setup. Destroy, like apply, will also check what's currently running and then create a plan of what needs to be removed in which order. So I hope this gives you a good high-level overview of Terraform and how it works. If you want to learn more such stuff, then subscribe to my channel and stay tuned for more videos like this. Thanks for watching and see you in the next video.
I like to work fast, and switching between all my work apps was slowing me down. With ClickUp, all my work is in one place.